All right, this is the last video for section 11.3. This is dealing with a couple applications given dot products. So the first one that we're going to deal with is back to the boat situation on a ramp. A 600-pound boat sits on a ramp inclined at 30 degrees, shown in the figure. What force is required to keep the boat from rolling down the ramp? Okay, the force that's happening to make it roll down the ramp is W1. So what I would like to do is let's go ahead and talk about what some of these vectors are. Let's go ahead and do the vector v. Vector v, even though it's placed down there, it could be put on top of w1, could put past it, do several things. Okay, so let's do f. The vector f is 0 and it's getting pushed down, so this is minus 600. All right, that's f vector. I would really like it if I had v vector. So v vector, if I look at this and I use the information here, I have this like angle, which means I can find the components of that vector by just saying cosine of that 30, comma, and then the y is always sine of that 30, right? Just components. Right? This is equal to cosine of 30 is radical 3 over 2. Sine of 30 is 1/2. So now I have f and also a v. Right? So I want W1 here. W1 is the projection of f vector onto v vector. Take a look at the picture. W1 is that projection. This is going to tell me how much force is being pushed down along the ramp. All right, so I write this definition out. V dot F over V squared times the vector V. All right, I'm just going to fill all this in as we go. V dot F. So I'm going to look at the ones above here. Okay, so I get up top, if I'm doing a dot product, I get 0 for the first component, and then I got negative 1/2 times, negative 600 times 1/2, which gets me negative 300. That is my numerator. The bottom is just V. Remember, V, the magnitude of V squared is just the dot product of V with itself. So looking at V, I got, what do we get? Let's go ahead and work this out over here, actually. I got radical 3 over 2 times itself, which gets me 3 over 4. Then I add it to 1 over 2. Squared, though, so it's 1 over 4. So I know this is equal to 1. That makes my life easy, your life easy. So that's the part in parentheses. I guess we could have done this. That's the non-vector part. Times vector v. Well, I have vector v, radical 3 over 2, 1/2. So W1 is equal to, I'm going to multiply negative 300 through there. So I got negative 150 rad 3, comma, negative 150. Right, that tells me how much weight, or the direction of W1. That would tell me how far that is, given that we have 300 or 600-pound boat sitting down. That's how much is in that direction. But that doesn't tell me actually how much force is being pushed down that way. To get that, I actually need to do the magnitude of said force. So this gets pretty big, but if you work all that out, you get 300 pounds. So we got lucky. The way it's split, the force, it's 300 here. And then it doesn't mean that 300 plus 300 gets to 600. Just the weight's distributed differently. But they didn't ask for that. They said, what force is required to keep the boat from rolling down the ramp? Well, W1 force is 300 pounds. And that's going down. So to maintain that weight, it would be 300 up. So we would need 300 pounds pushing up in the same direction of W1, but going the other way. So, and that force comes from here. We don't care about the gravity because we're not trying to get the, like this vector, right? or maybe even the orthogonal vector. This would be W2. Right here, right? W2 is the boat pushing down, but that just keeps the boat on the ramp. It doesn't keep it from going down. Do you see the difference? W1 pushes the boat down. W2 pushes the boat against the ramp. That's the gravity portion being split into two. So if I don't care about the ramp being pushed down onto the ramp. The boat down onto the ramp. I don't care. But I want to be able to keep the boat there, which means I need to fight this W1. W1 is 300 pounds. So if I wanted to fight it, I would apply 300 pounds. I like these problems. They look super complicated and they're not too bad. I would work this one a couple times. Check out the homework one that I gave you. Work it a couple times. Don't let these be something that you just watch me work or use a solution manual and be done with it. You're not going to do well when I place something else in front of you. Right, we're going to end this video with work. We're going to talk about it very quickly. In your physics class, you guys will get much more involved with work, but we can talk about work. Work W done by constant force, the vector F, acting along a line of an object is given by, okay, so we can tell how much work we need to be doing, right? I think work's measured in joules, I think, if I remember correctly. Magnitude of force times the distance, that's it. So if I know the force that's being pulled or pushed or whatever the force may be, and I know the distance that it's going to cover, I just take the magnitude of both vectors that do that and multiply it together. That's really nice on figure 1133 when the force is parallel with the plane that it's going to be pulled against or the distance it's being moved against. The force pulls it, but if it's in a parallel distance, then that's great. Right? It gets all of that. It's easy. Just multiply it. Now, the problem is most things when we pull it, I think about a wagon. I think about the force of a shopping cart. You don't really push parallel with the ground. Maybe you do a little bit, but I think we tend to just kind of push at an angle and take some of the force going parallel. So when that happens, so this box here, the force comes from here. This is like maybe like a wagon, right, with a handle, or anything with a handle, a cart that you're pulling by a handle. And we want the work done for that. Well, this box is being pulled to the right, P to Q. That distance is still happening. So if you look here in our formula for this one, we still have the magnitude of PQ. How far is it being traveled? How far is it traveling? How far is it being pulled or pushed? But the force in that direction is much different this time. The force of that direction is not F, but it's the horizontal component, this thing right here, that gives me all the force. So I want to use projection. I want to find that projection of that one, of F onto PQ. A couple of ways we could do this is the dot product of F and PQ. So if the force is parallel, we're going to want to use this. If force is not parallel, you can either use this one. I like that because it's pretty straight up. Or you could go and find the projection and multiply it by that, or the middle definition there. It's up to you. All the same. So they give us projection forms and the dot product form down there for definition of work. This is about as far as we're going to go into work for the time being. It may pop back up. This is the part I was talking about when I asked all of you who's had physics one, and a lot of you lifted your hands. Your physics are probably going to be a little more solid and more fresh than mine because calc just kind of skims by it really quick. It's like, hey, here's a nod to application. And then we go forward with more theory. Then a nod at application, and then theory. Let's do an example of this work stuff. They actually gave us a wagon. So the wagon is being pulled. Let's draw a picture. There's my wagon. All right, it's being pulled from here. Here's my handle. We'll call this point P. And we want to pull the wagon all the way. All right, we know it's this direction to this point, which is Q. Okay, it says a wagon is being pulled by exerting a force of 65 pounds on a handle, right, that makes a 20-degree angle. So 20 degrees, we'll call this F, the force, right? that one. We do know that the magnitude of said force, that's what they told us, is 65. I know the magnitude of that force is 65. I also can talk about the vector PQ. It just said it's pulling at 50 feet. So that means it went 50 feet in the x direction and 0 in the y. We need our F vector as well. All right, my F vector is the magnitude, 65, times the direction. Well, the direction is cosine of 20 is the x direction, sine of 20 is the y direction, right? So our component forms with the magnitude on the outside. The vector itself gives me the direction, tells me where to go. The 65 tells me how much. So I'm going to go a little further here so we can have both. I'm going to multiply cosine of 20 times 65. Let's leave this just like this, because I don't want to make any rounding errors until the very end. Well, hopefully no rounding errors, but if I wait till the end and don't do any kind of decimal, then I can avoid it. All right, there's F. I'm going to write down PQ again, because we're going to need both. All right, it says if I want to find work, I really like the formula of the dot product. Makes it very easy. So the dot product, right? If I multiply, we do, okay, I know the back half for sure is going to be plus 0, right? This times that is 0. The front, if I do the multiplication, I'll leave it as a exact answer for a moment. Let me move this plus 0 over. We get cosine of 20 degrees, and then plus 0. I can figure this out. I think I said joules. Our book's going to measure this by foot-pounds. Make sure a couple things when you're doing foot-pounds for this. Any kind of these problems, you're going to get it wrong in the book if you don't convert this to pounds, whatever the force is, and convert the distance to feet. There are some other ones. I think there is something meter. Maybe it's a pound meter or something like that for our metric. I don't know if they still use a pound on that. Like I said, this is a nod towards physics because we are doing essentially a bunch of physics with trig, and then we're going to apply some calc to these vectors here in a moment. But here's our nod application.